Hi, welcome back. This is the second part of a lecture on chapter 22, and we're gonna pick up this time on the topic of RC time constant. RC is for resistance and capacitance. Okay, as we mentioned in the previous video about the LR time constant, there is a transient response for inductive circuits, and there is also a transient response of capacitive circuit, and it is measured in terms of the product of the resistance times the capacitance. So to calculate the time constant on a capacitive circuit, we multiply the resistance times the capacitance, and of course the resistance must be in ohms and the capacitance in the units of capacitance, which is the farads, and the result of that product will be the time constant, and this is expressed in seconds. Okay, so let's now take a look at the capacitive circuit with the resistor in it. And we have the situation very similar to the one that we had with the inductors. So for the capacitors as well, you may recall from previous lectures when we talk about capacitance, the capacitors, they act as a short circuit before they're fully charged. Once they're fully charged, then they act as an open circuit. So if we take a look at this circuit right here, okay, it is open, so there is no current going through the circuit. Okay, no current because we have this opening here. So when there is no current, so nothing goes through here, the capacitor is not being charged. Okay, if we did not have this capacitor here, if that did not exist, and instead we have just a short circuit here, the very moment when we close the switch, okay, the 100 volts will be applied to the 3 mega ohms resistor, and then the current on the circuit will be the 100 ohms divided by the 3 mega ohms, and that will give you 33 times 10 to the minus 6. Let me see, yeah, minus 6. Alright, so that will be like 33 microamps. That would be the current on the circuit. However, we do have this capacitor here. Okay, so when we close this, remember the capacitor will act as a short circuit until it is fully charged. When it's fully charged, then the capacitor will act as an open circuit, and the whole voltage will be this capacitor will actually be charged with the matching voltage, not exactly to the voltage source in this time because we have this capacitor, but we apply a voltage divider. If we apply a voltage divider right at this point right here, then that will be the voltage across the capacitor, and will behave in the same way that the inductors behave. Okay, so before the voltage on the capacitor, on this capacitor here, once the switch is closed, okay, is supposed to be the 100 volts that are here on the source. However, it takes a while before the capacitor charges to that point. Okay, and it will take, and it will behave in this. Okay, this is the transient response. Okay, and it will take 5 time constants before you get to that point on the charging capacitor. Okay, so in this case, the time constants will be the resistance times the capacitance. The resistance here is 3 mega ohms, and the capacitance is 1 microfarad. So 3 mega ohms will be 3 times 10 to the 6, and the 1 microfarad will be 1 times 10 to the minus 6. So the plus 6 and the minus 6 cancel, and 3 times 1 equals 3, so it will take 3 seconds before this capacitor is charged to 100 volts. Okay, when one is charged to 100 volts, 100 volts, it will remain like that. It will remain at that value, okay, because basically at that point it will act as an open circuit, so and all the potential will be dropped across the capacitor. So similarly, when the capacitor discharge, okay, let's say for example we apply the 100 volts in the circuit, we close the switch, it will take 3 seconds for the capacitor to fully charge, and at that time the capacitor will hold all the voltage in it, and it will remain like that, okay. But let's say, and then we open the circuit and we short this capacitor. Now we have a capacitor that has the circuit that only has the capacitor and the resistor. The voltage source in these circumstances is not going to play any role in the circuit. Okay, so what's going to happen now, the capacitor is fully charged at this time, and then we close this switch right here, then the capacitor starts discharging through the resistor in that direction. All right, and now the voltage on the capacitor at the time where we start will be 100 volts, and then it will start discharging like this until it gets to fully discharged to 0 volts. Okay, now what the time constant have to do with this, and what is the role of the time constant? Same as the inductor. The time constant is, in this case, is the resistance times the capacitance. It takes 3 seconds. I'm sorry, I misled you when I say that 3 seconds will take for the capacitor to fully charge. It will take 3 seconds for the time constant. This is the time constant right here, the 1 times constant, and that will be 63% of the targeted value. Okay, in 1 time constant, it will charge up to 63% of the steady value of the voltage. Okay, so it takes 5 time constants for the capacitor to reach the value that where it needs to be, which is the value of 100 volts in this case. Okay, and when it discharges, it happens the same thing. Okay, so it will be fully charged. We close this the switch right here, then the capacitor start discharging through the resistance, and it will discharge in this rate until it gets to 0. Now, at the first the first time constant, okay, the first time constant right here, it will discharge 63% again, 63%, and then the rest will be discharged in the other 4 time constant. But it will take a total of 5 time constants for it to discharge all the way. Okay. So back to the actual lecture. Okay. Here it is. Okay, we have this the time constant for the capacitive circuit will be calculated with the resistance times the capacitance, and in this example we have a capacitor and a resistor. So on this capacitive circuit right here, we have a source of 100 volts on a DC source. The switch closes at time 0, and then at that time, if we didn't have the capacitor, then the current will be instantaneously. But since we have this capacitor there, it will take a little bit of time for the capacitor to fully charge. Okay. So this 100 volts will be reflected on this capacitor, but after a short while. Okay, so it will take from 0 to, if we already calculated that the time constant is going to be 3, so for the first 3 seconds it's going to go up to 63% of the total, which is 100, so it will be 63 volts, and then after it will continue until it reaches the full charge of 100 volts. Okay, this is that is the voltage on the capacitor. Okay. Similarly, once the capacitor is charged, we can open the switch right here, and we can put another wire here to short this to make the circuit just be this loop right here. This source now plays no role in here because it's open. It's basically, it has been disconnected from the circuit. Okay, so this is the circuit now, but this is fully charged at 100 at this point. Okay, and let's say we start at this point. Let's say we do the time, what is called the transient response time. Okay, with 5 times constant. The time constant is 3, so 3 times 5 will be 15 seconds. You know, so the capacitor will charge for 15 seconds, and then at that point it will reach the maximum charge right there. And let's say at that point we turn the switch off, and we connect this wire right here to short this circuit like this. And now at that point the capacitor will discharge, or will go this way until it gets to the 30 seconds. Okay, so it will take from 0 to 15 seconds to charge, and then if we turn it off right there and then and short this circuit like this, then the capacitor will discharge at a rate of 5 time constants. Okay, the first time constant will discharge 63% of it. So we'll go from 100 to 37, and then we'll continue until it gets to 0. But all this process is going to take 5 time constants. Okay, the first time constants though will get you 63% of the voltage discharge. Okay, so now this is the discharge, the same curve that we did in the previous slides. Okay, so just like when we did the capacitors, I mean the inductors. Remember that we have an inductor, we have it, it has a transient response, a time constant, and then when we open up the switch, we disconnect the voltage source from the circuit, then the inductor discharges and generates a very high voltage because of the quick change rate of change on the current. So a capacitor can be charged slowly by a small charging current through a high resistance, and then be discharged quickly through a low resistance to obtain a momentary surge or pulse of discharge current. Okay, so basically so the circuit on this picture illustrates the application of a battery capacitor, okay, unit to a flash bulb for a camera. Okay, so basically this is what they're saying. Okay, if you have a 15 volts battery, you can connect it to a capacitor here, through a resistor of 3 kilo ohms, and then after the certain time, 5 times constant, this will be fully discharged. If we disconnect the source, we open the circuit at that point, and then we connect this capacitor to another load. In this case, we can connect it to a bulb, and then close the circuit. This one will generate a very high current through here. Okay, this case will be 5 amperes. If you can see right here, the current right here will be like 15 divided by 3000. It's going to be a very small current, but in this circumstance, once you have the 15 volts on the capacitor, then you can have a very small resistance, and you can have higher current in this way. And here are some of the wave shapes when it comes to capacitors. Okay, let's say for example we have a voltage source, okay, And this voltage source is a pulsating source. It's not constant 100 volts, but it will go 100 volts for one time constant, then it turns off, stays off for another time constant, then goes and apply another 100 volts for the time constant, and so on. Okay, so it's gonna be a waveform on this shape, for the voltage. Now this input of the voltage right here, this 100 volts is gonna be pulsating. It will be like 100, 0, 100, 0, and so on. Okay, this will charge the capacitor in this manner. Okay, when you first turn it on, it will charge the capacitor up to 63 volts. Even though the voltage applies 100 volts, it's only on for one time constant, right? So the capacitor will charge at a rate of, for one time constant, will be only 63% of the applied voltage. So in this case, because this is 163% of that, the capacitor will be charged up to 63 volts when the voltage turns off. When it turns off, then the capacitor starts discharging again. At this point, the capacitor only has 63 volts in it. One time constant. During one time constant, the capacitor only discharges 63%. So it will discharge 63% of the 63 volts in here. So it's going to go down to 23.3 volts. This will be the charge in the capacitor by the time the voltage gets turned on again. Okay, at that point you apply 100 volts. Okay, we apply 100 volts and the capacitor will charge again 63% of the difference. Okay, so it will charge 63% of the 100 volts, but you have 100 minus 23, so basically there's only a 70 some volts difference. So from there you're gonna charge 63% of that amount, and that will bring it up to 71.6, and then it turns off again to go back to zero. The voltage goes to zero, so the capacitor starts discharging again. At 71 volts, it will discharge 63% of this amount, and that will bring it down to 26.5, and then 100 minus 26.5. Whatever that is, 63% of that will be the next charge. Okay, and it will continue like this. It's the same, very similar situation when it comes to the current. So if the switch is on, basically you turn this on, and then the current is going to go through this circuit. Okay, the capacitor, let's say, is not charged at the moment, so the current is fully flowing through the circuit. As the capacitor charged, that the current start decreasing as well, so it will be from the 1 amp start going down. See, it will go down 63% because the time where the switch is on is only one time constant. Okay, 63% goes down there, and then the switch here will open, and this one will close. So basically no voltage being supplied to the circuit, but the capacitor has voltage on it. It will start discharging the other way, so that way at that point the current will be at negative 63, and it will go up 63%. It will stop right here, and then at the very moment the switch turns back on, the voltage gets applied again. It jump 1 milliamp, but because it's down here, it only gets to 0.76, and then from that point on, as the capacitor starts charging again, the current starts going down. It will go down 63% of this amount, so it will bring it to that amount, and then the power turns off. Then the capacitor is basically charged at this point, and then it starts discharging, and the current start changing also. Okay, so it keeps doing this pattern over and over and over. Okay, it's the same thing we can see here with the voltage across the resistor. Okay, At first, when you turn it on, the voltage across the resistor is the fully 100 volts, but because this one basically has nothing in it. But as this one starts charging, start taking away voltage from the resistor, this 100 volts start getting divided between the resistor and the capacitor, so the voltage across the resistor start decreasing, and it will decrease by 63%, because again it's only one time constant. Okay, the switches are on and off every time constant. So, and then at that point, it drops all the way to 63, and it start going charging again. This is when the capacitor, when the voltage source is disconnected, the capacitor is now discharged through the resistor from the other direction. That's why it's negative. Okay, and now the voltage on the capacitor start discharging on the resistors, and now that's why it goes up like this. And then the voltage source comes back on. That's 100 volts. So from here, 100 volts will bring it up to this point, and now the capacitor start charging. So the voltage on the resistor start decaying. You just got to continue doing this. Okay. And when we have a long time constant, okay, so if we have a long time constant, let's say for example the time constant is very long, either because that the capacitor is large or because the resistor is large. So this will be the voltage on the capacitor. Okay, it will never get down to 63%, because let's say from here it's not even a full time constant. Okay, so the voltage is being applied on and off. This voltage right here is on and off on the circuit, but the time constant of the circuit is very large. So by the time this one might be very small compared to the time constant, and that's why the capacitor basically looks like the voltage on the capacitor will start looking like a constant voltage. And if the time constant is very short, then it start fully. Now we're looking at the voltage on the resistor. Start fully, and then goes like this. Then goes down, goes back up, goes down, goes back up. Okay, so these are the effects of the voltages. So on this one is the voltage on the capacitor, the voltage out basically when you have a very long, relatively long time constant. And when you have a very short time constant, let's say we want to measure the voltage here on this resistor, we take it from here, and it will be like that. It will be the full load at first, then as the source turns on, start charging the capacitor, then the voltage on the resistor start going down. Okay, and it will go all the way down to 0 before the next pulse on the voltage source goes to 0. Once that it goes to 0, then the capacitor starts discharging through the resistors. Okay, and it gets to 0 like before the voltage turns back on, and they just keep on doing this. This is just example of how this wave can be, can behave, according to the time constants. Okay, now. In this figure, this figure illustrates the charge and discharge of an RC circuit with short time constant. Okay, note that the wave shape for VR, the voltage on the resistor, and section D, which is the one in the bottom, this one right here, has sharp voltage peaks for the leading and trailing edge of the square wave applied voltage. Okay, let's this is the applied voltage, okay? From here. This is the applied voltage. It stays at 100 volts for 0.02 seconds, then is no voltage applied for another 0.2 seconds, then turn back on and apply voltage of 100 volts again for the following 0.02 seconds, and so on. This is the voltage that is being applied from the source. So this is how the voltage on the capacitor will behave. When we apply this voltage here, we will be expecting to have 100 volts put on the capacitor, right? But it takes a little bit of time for this capacitor to charge. So this right here is the delay, right there. So if it was a pure resistor, it would go like this and then like that, okay? But now we have a delay here, so that is the delay. Now the capacitor is fully charged and remains charged until the voltage turns off. When the voltage goes to zero, then the circuit continue providing voltage, but now the voltage is going to be from the capacitor. Now the capacitor will discharge to zero, but it's not going to be instantaneously. See, it's going to take a little bit of time before it gets to zero, and then will be totally discharged. And then the voltage is applied again, then the capacitor charge again, but again it takes a little bit of time, okay? It's not instantaneously. So when it gets to the 100 volts, then we remain like that until the voltage gets turned off. Now the one that's supplying the voltage to the circuit will be the capacitor, and this one is going to discharge all the way to zero within this time of this period of time right here. Okay. Now what about the current on the circuit? Okay. So when this thing is discharged, okay, there is no charging here. You apply we apply the voltage, so the current will be fully running through the circuit. So it will start right there. Okay. But as the capacitor starts charging and start blocking the current until when it's fully charged, then the current stops, because remember, the capacitors, when they're fully charged, they behave like a short circuit, like an open circuit, okay? And now in here will be no current from the moment this one is charged until the voltage applied is turned off. So when that is turned off, what happens is that this is no voltage applied here, so acts like a circuit, like a short circuit. Now the voltage that's in the capacitor start discharging through the resistor, so, and the current start flowing from the other direction. That's why it goes all the way down to fully charged, but in the negative direction, and start discharging again, so the voltage start getting reduced until it gets to zero. Fully discharged, gets to zero, and then we connect we apply the voltage again. Now the current jumps again to 1 amp, and then start discharging as the capacitor charges until it's fully charged, then no current goes through it. Disconnect the voltage again. Now the voltage is being supplied by the capacitor at maximum on the opposite direction, and start discharging again until it gets to zero. Okay. That's the behavior of the current on the circuit that has a pulsating voltage source with a capacitor in it. And the voltage on the resistor basically behaves in the same manner as the current, because remember, the current and the resistor, they're in phase, so they're proportional. Okay. So whenever the current is high, the voltage will be high because the resistance is constant. So we have high current, we have high voltage. We have no current, well, we have no voltage on the resistor, and so on. Okay, and here is one with a very long. This was with a very short time constant. Okay, so the time constant, as you can see, is very short compared to the pulsating voltage. This is the time that the duty time of the voltage, but the time constant is very small. See that? So from here to here, that is 5 time constants. So the time constant is very small. Now, when the time constant is bigger than the duty cycle of the voltage, then as you can see, this is supposed to be 100 volts, right? So the voltage in the capacitor is supposed to charge up to 63% on the first, up to 63 volts on the first time constant, right? But the time constant here seems to be very large because on the first duty cycle of the voltage, the capacitor only gets 0.5 volt charge, and then the voltage turns off, it starts discharging and then charging again. But as you can see, it never passes a high, not even close to the 63%. Okay. Same with the current. So the current starts discharging here, but just a little bit because the capacitor gets really no opposition, okay, to the current. And in the negative side, it will be just a little bit as well. See that from here to here, the difference from here to here is very small. So it gets discharged, but just a little bit. When it's in the negative side, it gets up, but just by this amount. See that? See how small this? Okay, and that is because the time constant is very long compared to the duty time of the voltage. Okay, so the voltage is being applied on and off, on and off, on and off, but the switching period is very small compared to the time constant of the circuit. Therefore, the voltage on the capacitor basically, even though this is a pulsating voltage, this one basically looks almost constant. Okay, and that is due to the fact that this is a very large resistor, or this one, it could be considered also a large capacitor. Okay, remember the time constant on the capacitor circuit is R times C. So the transient voltage and current values can be determined for any amount of time with a universal time constant chart. There are some charts like in here, see that? And the analysis of this chart and a very, you know, later on in your career, you're gonna be studying some advanced techniques on how to analyze time constants. Okay. All right, and at the end of the chapter, we do have a couple of tables here for comparison purposes. Okay, that will mark the end of chapter 22, and thank you very much for your attention and the opportunity to serve you.